Pressure example. A tire pump has a piston whose cross-sectional area is 0.001 meter square. If we apply a force of 150 Newton to the piston, find the pressure on the air in the pump. So we know the pressure formula is P is equals to F over A. So we know the force acting upon and we know the area. So all we need to do is just plug it in the formula and find out the pressure. So it's nothing but 150 over 0.001. That will give you 1.5 times 10 to the power of 5. So we could write this 10 to the power of 5 as 10 to the power of 2 times 10 to the power of 3. And 10 to the power of 3 is nothing but kilo. And so we can write this as 150 kilopascal. So this is the picture representation, like the person is using 150 newtons pressure on the cross-sectional area of the piston is 0.001, and the pressure on the air is 150 kilopascal. Atmospheric pressure. Atmospheric pressure at the sea level averages 101.3 kilopascal, which is approximately 14.7 pound per square inch. Meteorologists use HPA, which gives the same number as the old unit, the millibar. The instrument which is used to measure the pressure is called the barometer. And let me show you how the barometer pressure looks like. So when you have low pressure, just like the plungers, like you'll have this plastic thing will be high puffed up. When there is no pressure, it will be like this, and when there is any high pressure, then it will be pressed back into something like a seal chamber, and you will have high pressure, which is denoting which is denoted by the pressed thing right here. So whenever you see a barometer, you will hear something like 760 millimeter or 76 centimeters or things like that. That just because they measure the bottom part right here is the mercury. So mercury, we all know that even though it is metal, it's in the liquidous phase, and so they have this one. So whenever there is any pressure, so the mercury from here fills up in this tube right here. So we measure the height of this level, and so based on how how much is the level of it, like you can see in the scale right here, ruler, you can see the measurement as something like 32 or 33 like that. Oh, sorry, right here it's 28, close to 28. So that's what they say as like 28 centimeters or things like that. So that's what is the pressure they talk about. So you can see that there is a mercury at the dish, and this is the mercury column, and this whole thing is a glass tube, and this is the ruler right here. And so whatever the empty air right here, that is the place where this air pressure is measured upon. And the air pressure causes this mercury column to raise in this tube, and it feels like this. So final height of raising mercury column, whatever that gives you the measurement of how much is the pressure we are trying to measure. Okay, water pressure. The water pressure at any point in a liquid depends on the distance below the surface, and it is measured by d, g, and depth. D is the density, and the g is the acceleration due to gravity, and then depth. Depth is the distance below the surface. The upward force exerted on an object immersed in the fluid is called the buoyant force. Just like you have a cup filled with the water, and then if you try to poke a pencil inside of it, or you try to put a pencil, it always pops back up. So that pops back up because the water pushes it outside, like an upward. So that force which is making the pencil pop up is called the buoyant force. Okay, this buoyant force is always works upward, and it is measured by dVg. And since it is a force, it will have still the same units as newtons to measure the buoyant force, and d here is the density, and V is the volume of the fluid displaced by the solid object. So whenever you have a felt object, if you try to immerse an alien object or new object into that, so how much ever the water displaced, that is the volume we consider here. And G is acceleration of gravity, which is 9.8 meters per second square. Buoyant force, as I already said, buoyant force is always an upward force, and because the pressure underneath an immersed object is greater than the pressure above it, so that's why it always pops back up, and the buoyant force works upward. Archimedes principle. Archimedes is the first one who talked about measuring the density of the irregular shaped objects, and buoyant force on an object in a fluid is equals to the weight of the fluid displaced by the object. This is what he figured out with his experiments, that the buoyant force, which is the upward force, is always equal to the weight of the fluid which is displaced by the object. When the container is full, if you try to put some water, so how much ever is the weight of the water, that would be the force which was applied on that object. So something like, if you are trying to immerse this object right here, and the weight of this object is always working downward, and how much ever is this weight right here, equivalent to that would be some force which would be working as a buoyant force, which will try to make this go up, or kind of go a little bit higher. And this pressure is greater at the bottom of the body than top. Whatever the pressure right here is higher, that's why it will be pushing it up. Gas laws. The macroscopic behavior of gases can be described by three laws. One is Boyle's law, Charles' law, and third one is the ideal gas law. Both of the Boyle's law and Charles' law are named after the scientists who proposed them, and ideal gas law is the combination of both Boyle's and Charles' laws. A volume of gas is inversely proportional to its pressure when its temperature is held constant. So Boyle's law tells you that as long as the temperature is constant, whenever you increase the pressure, then the volume will be lowered. And if you lower the pressure, then volume will be increased. So in other words, pressure is inversely proportional to the volume. So the same thing can be expressed by P1 divided by P2 equivalent to V2 over V1. P1 and P2 are the initial and the final pressures, and V1 and V2 are the initial and the final volumes. So when you look at this picture right here, you have a pressure 100 kPa is used on this piston right here, and at this time the volume is 1. So according to the Boyle's law, he says the product of P1 V1 should be same as long as you have the same gas filled in this container right here. So let's see what is P1 times V1. The product of P1 and V1 is nothing but 10 to the power of 5. So the same gas, this time what I want you to do is I want you to double the pressure. So this time the pressure became 200 kilopascals. So when obviously the pressure is inversely proportional to the volume, so the volume has to go down. As expected, the volume is become half of it, which is 0.5 meter cube. So now according to the Boyle's law, the product of P2 times V2 should be exactly same as P1 times V1. Let's see if it is same. So P2 is 200, 200 times 0.5 gives you the exact same number, which is 10 to the power of 5 here and here. So let's see, test again further. So that is, you increase the pressure much further, which is 1000 kilopascal. The time the volume has become much smaller and the volume became 0.1. So when you multiply P3 times V3, then you get 10 to the power of 5. So from here, this experiment, you can see that P1 V1 equals to P2 V2 equals to P3 V3. So as long as you use the same gas and you're keeping the temperature constant, the product of pressure and volume remains constant per that particular gas. The volume of Charles' law is the volume of a gas is directly proportional to its absolute temperature. So when we say absolute temperature, we are not talking about the temperature in degrees Celsius or degree Fahrenheit. We are talking about the temperature being in degree Kelvin. Okay. So in this case, the volume is directly proportional to temperature. It means as you increase the temperature, the volume increases. As you decrease the temperature, it compresses. So you can see in this picture right here, so you're keeping the pressure same. But when you look at the temperature right here, this is at 0 degrees Celsius, which is equivalent of 273 degree Kelvin. And the volume is 1 meter cube. So in this case, you are trying to reduce the temperature. So you're freezing it, but you're keeping the same amount of pressure. You're not changing any pressure. So when you're decreasing the temperature, you see that the volume also decreased. So the same gas, if you are trying to increase the temperature, so you almost um, double the temperature. So you can see that the volume has become so much more than the first or second. So you can see that as the temperature is changing, the volume is changing in such a way that if the temperature increases, the volume increases. If the temperature decreases, the volume decreases. You can see this graph right here. As the temperature is increasing, the volume is increasing. It is a linear relationship between the temperature and the volume. And you can see that the temperature is measured in absolute temperature, which is in degree Kelvin, and the equivalent of degree Kelvin is also given here in the degree Celsius. So 0 degree Celsius, when you represent in degree Kelvin, it is 273. So any temperature mentioned in degrees Celsius, you add 273 to that, you get the value in degree Kelvin. Absolute temperature. Absolute zero is negative 273 degrees Celsius. And when we say absolute zero, it is not 0 degrees Celsius or 0 degree Kelvin. I'm sorry, absolute zero is not 0 degrees Celsius or 0 degree Fahrenheit. It is 0 degree Kelvin. Okay, absolute temperature, absolute zero is 0 degree Kelvin. And it is theoretical but unreachable lowest possible temperature. Since the temperature is proportional to energy, negative temperature makes sense. And absolute temperature is measured in Kelvin. It is named after Lord Kelvin, who lived from 1824 to 1907. And when you look at the thermometer, just like the degree Celsius and degree Fahrenheit, it will look the same. Only thing is that the markings will be different. So when you have negative 273, that's when you will have the 0 degree Kelvin. And as you go up 0 degree Celsius, let's say that 273 degree Kelvin would be right here. And 100 degrees Celsius will be somewhere right here, and that will be equivalent of 373 degree Kelvin at that the water boils. The next one is the ideal gas law, which is the combination of Boyle's and Charles' law. The ideal gas law combines Boyle's and Charles' laws into a single formula that is nothing but P1V1 over T1 equals to P2V2 over T2. The temperatures, of course, are again used in absolute scale, which is degree Kelvin. Gas molecules are very small compared to the average distance between them. A gas is mostly empty space. So that is because the distance between the molecules is too large. It is easier for the gases to compress, and it could be mixed with other gases too. And the mass of a certain volume of gas is much smaller than that of the same volume of a liquid or a gas. Collisions: gas molecules collide without the loss of kinetic energy. Gas molecules exert almost no force on one another except for when they collide.